Whenever you're dealing with the real world, things are rarely simple. Just about anything worth studying has lots of interconnected components. And that means that when we model them, we need to often use functions that themselves depend on other functions. How can we deal with that more complex behavior when we're looking at derivatives? We've seen a number of different ways of thinking about the derivative thus far. Conceptually, by thinking of it as the sensitivity of a function to changes in its input, or sometimes as the rate at which that function changes. Numerically, by thinking of it as the ratio of those changes as those changes get smaller and smaller and smaller. Geometrically, by thinking of it as the slope when we zoom in infinitely close to part of a graph. And finally, algebraically, by looking for patterns in derivatives of different kinds of functions. In some sense, this last way of looking at derivatives is the most powerful, because it saves us from doing a lot of tedious calculation work, letting us find the derivative of a function instantly, at all points all at once. Simple linear functions and constant functions act exactly the way we expect them to, based on our previous intuitions about slope. The power rule, along with the sum and difference rules and the constant multiple rule, let us deal with an entire class of power functions and polynomial functions. Finally, by analyzing the graphs of a few other simple functions, exponential, logarithmic, sinusoidal, and so on, we can figure out their derivatives. These are great, but if we want to model real-world situations, they're not going to be enough. We're going to need to see what happens when we start combining these functions together. Ever been on a Ferris wheel? They're pretty fun, especially if you're at a place with a good view, and you're not afraid of heights. We can model how high a rider is off the ground by using a sinusoidal function, like this. In this case, the coefficient inside the function, 0.2, is used to control how fast or slow the ride goes. Now suppose you're on this ride, and you want to know how fast are you rising or falling 6 seconds after the ride starts, because I know that calculus is on your mind when you're in an amusement park. So that's exactly the sort of thing you'd use the derivative for. There's just one problem. The thing inside the cosine function is itself another function. We've never had to deal with that when we're doing derivatives. If that 0.2 weren't there, we'd have a much easier time. If only we could get rid of it somehow. What do we do? Well, according to James Tanton, one of my favorite math YouTubers, there's a great life lesson here. If there's something in life you want, make it happen, but then deal with the consequences. See, we'd really like to have just a single variable inside our cosine. So what we could do is define a new variable, say call it u, that just happens to be equal to 0.2t. That would let us just write cosine of u in our function. In fact, we can say even more about the units of u. Cosine, remember, is a trigonometric function, which means it usually takes an angle as an input. That means that u is actually measured in radians, not degrees, by the way. In calculus, we always work in radians. Anyway, knowing that, not only can we find that dh over du, the derivative of h with respect to u, is 25 times sine u, but we can actually describe the units, feet per radian. So that tells us how h is related to u, but we really want to know how h is related to t. So we still need to do some work. Well, we can see how u is related to t by taking du over dt. That's just a linear function, so its derivative is 0.2, and its unit is radians per second. So how does that help us find dh over dt? Wait a minute. We know how h is related to u, and we know how u is related to t, so if we combine those derivatives together by multiplying them, those du's should cancel out, and we'd get dh over dt. So we take dh over du, which is 25 times sine of u, multiplied by du over dt, which is 0.2, and if we multiply the units together, feet per radian times radians per second, we do in fact get feet per second. But we're not quite done. Our unit is feet per second, but remember, u is measured in radians, not seconds. We still need to deal with the consequences of our definition. And that means remembering that u was actually 0.2 t all along. If we clean that up just a bit, we find that dh over dt equals 5 times the sine of 0.2 t. Okay, let's not forget to solve the original problem that we asked when we were sitting on the Ferris wheel. What's happening at t equals 6? Well, if we plug that in, we get about 4.66, and that means that 6 seconds after the ride starts, you're rising at a rate of about 4.66 feet per second. Food for thought when you're on the way back down. Let's take another look at what we did, but this time more in general, without any preconceptions about what actual functions we're using. What we really had was a composition of functions, one function inside another. We can think of f as our outside function, and g as our inside function. To make our life easier, we gave that inside expression g of x a new name, say u. Now y equals f of u, and u equals g of x. Each is just a simple function. Then, to find our derivative dy over dx, we can find our simpler derivatives dy over du and du over dx, so that when we multiply them, the du's cancel out, and they give us the derivative we actually want. Now we can write dy over du as f prime of u, and likewise we can write du over dx as g prime of x. Finally, to get everything back in terms of x, we have to replace u with g of x, which is how we defined it in the beginning. What we end up with is a result called the chain rule, which lets us differentiate composite functions, basically functions inside functions. The idea is we only take one derivative at a time. First, we differentiate the outside function f while leaving the inside g alone. Then, we multiply by the derivative of the inside function, which is g prime of x. Now, at this point, it's okay to let your jaw hang open a little bit and go, oh wow, that's a lot of symbols there. That's a valid feeling in math. I still get it myself when I learn new concepts. So it's worth it to take a moment to understand why we're using all these symbols. The chain rule is giving us a general way to deal with the derivative of any composition of two functions, no matter what those functions are. It's essentially a recipe in symbolic form. But if you're anything like me, the thing that really makes a recipe like this click is an example that shows it in action. So let's do one. Check out this function. You've got x squared minus 5x plus 1, and then that entire thing is raised to the fourth power. How could we find its derivative? Well, it is a polynomial, so if we really wanted to, we could do a bunch of algebra to expand the whole thing out, and then use the power rule a bunch of times. But remember what we said last time, a good mathematician is lazy. That sounds like too much work, so let's try to find a quicker way to do it. What we really have here is a function inside a function. The outside function is stuff to the fourth power, and that inside stuff is x squared minus 5x plus 1. So we can make short work of it with the chain rule. First, we take the derivative of the outside function, leaving the inside stuff intact. The derivative of stuff to the fourth power is 4 times stuff to the third power. Then we multiply by the derivative of that inside stuff, which in this case is 2x minus 5. There we go, we're done already. That's a much cleaner way to take the derivative. Now, if we really wanted to, by the way, we could still do that substitution like we did before, setting that inside stuff equal to a new variable, say u, and multiplying the simple derivatives together. But if you can identify the outside and inside functions, you don't need to do that every single time. You can just use the chain rule as it's written. Now, I understand that might have been a lot to take in. You might not have gotten it on your first try. If not, go back and watch it again. Pause it once in a while to think through what's happening at each stage of the reasoning, until you can convince yourself that it makes sense. See, that's actually one of the big reasons I'm making these videos, so that you can go through it at your own pace. Take the time you need to understand what's going on, and then figure out what parts of the process might be giving you trouble. Calculus isn't easy, but if it were, it wouldn't be interesting. It is worthwhile for two reasons at least. First of all, it allows us to describe so many real-world phenomena and how they change. And second, it gives us a chance to take a step back, look for patterns and structure, and see how everything is connected.